In these videos, we're gonna talk about group cohomology. Note that for profinite group, there's another notion of group cohomology that better captures the profiniteness, and we'll discuss that in later videos. For now, let us just fix any general group G. Now, one way to study G is via its action on other abelian groups. For example, in representation theory, we would study the action of G on vector spaces. Or in number theory, we often look at the Galois group of a Galois extension L over K acting on the multiplicative group of L. Now, every abelian group with a left G action could also be viewed as a module over a ring. Which ring? Well, we can define the group ring ZG, which as a Z module is just freely generated by elements of G. That is, its elements are just finite formal sums of element of G with coefficient in Z. Alternatively, we can think of its element as functions from G to Z with finite support. For example, this element would correspond to a function that sends G1 to 2, G2 to 3, G3 to minus 5, and everything else to 0. Now that's the additive structure of ZG, and then we can define multiplication on it in the obvious way, turning it into a ring. Thus, every abelian group with a left G action could be viewed as a module over some ring. But what's the point of that? What's the advantage in doing that? Well, it turns out that the category of modules over any fixed ring is abelian. If you don't know what that means, don't worry. Just think of it as a fancy way of saying that the category has good notion of kernels and co-kernels. In particular, in an abelian category, we have short exact sequences. Short exact sequences are a great computational tool because they allow us to deduce information about one of the terms from the other two terms. Now, one way of studying the group G is by looking at G invariant. More specifically, given a short exact sequence of G equivariant maps of ZG modules, we can look at the induced map on the G invariant submodules. Now, since L here is just the quotient of n by m, we might expect that the G invariant submodule of L is just gonna be the quotient of ng over mg. But unfortunately, that turns out not to be true. More specifically, the G invariant functor, which is a functor from the category of ZG module to the category of abelian groups, is left exact but not right exact. In other words, it preserves injectivity, but it does not preserve surjectivity. So in particular, it does not preserve short exact sequence, and we say that it's not exact. Now we'll define the cohomology groups of G in a way that will allow us to extend this sequence into a long exact sequence of cohomology. In particular, we can view the first cohomology functor as measuring the extent to which this functor here, this G invariant functor, fails to be exact. And then the second cohomology functor could be viewed as measuring the extent to which the first cohomology functor fails to be exact, and so on. Now our discussion will actually apply to any general left exact functor between abelian categories. Such a functor will preserve injectivity but does not preserve short exact sequence, and we can extend this sequence to a long exact sequence using something called the right-derived functors of f. The first right-derived functor of f measures the extent to which f fails to be exact, and then the second right-derived functor of f measures the extent to which the first right-derived functor fails to be exact. These group cohomologies are then just the right-derived functors of this G invariant functor. So what are these right-derived functors? We'll explain this in the next video.